Welcome to lesson 6, what about other bases? We're going to be exploring exponent patterns with bases that are not 10, which is what you've seen in the last several videos. Today's criteria for this video is to use the exponent rules for bases other than 10, and that's how you'll be successful. We start with a true or false, comparing expressions with exponents. You're given a list of 4 different expressions. Take a moment here to pause and decide whether they're true or false, and be sure to have a reason as to why you said true or false. Now that you've paused and had some time to do that, let's go through these. So the first one, 3 to the 5th is less than 4 to the 6th, is a true statement because the base and the exponent are both smaller on the left side. Now, maybe you went ahead and you evaluated each side, which is still a fine strategy, but just kind of looking at that base and exponent, you should be able to determine that it's true. Number 2 is actually false. When you square a negative, the result is positive. So -3 times -3 is a positive 9, and 3 times 3 on the right side of that inequality is also positive 9. So those are actually equal to each other. This is again false because when you cube a negative, the result is negative. So on the left side, that would result in a negative answer. And on the right side, it will be a positive answer. So we would say that that's false, and it would actually be less than. And the last one is true. When you have -5 squared, you end up with a positive, and a positive is always greater than a negative. So that last one, because the negative is not included in the base, meaning it's not in the parentheses like you see on the left-hand side, that means that you're only squaring the 5 and not the negative. So 5 squared is 25, but then it's still a negative because the negative was not included in the base. That'll kind of come up again later in the lesson, so just keep that in mind. So just think, would the same strategies have worked if all of the bases were 10? And yes, all of the same strategies that we used would work. Powers with a base of 10 behave the same way as those with bases other than 10, so we could still reason through these different situations if the bases were all 10. Moving into the next one, we're going to look at what happens with 0 and negative exponents. So we start with a table very familiar to what we've seen in the past. So you're going to complete the table to show what it means to have an exponent of 0 or a negative exponent, and then go ahead and answer questions 1 to 6. So take a minute here to pause the video and work through that activity. Now that you're back, let's kind of go through this together and analyze what we came up with. So the first question says that as you move towards the left, each number is being multiplied by 2. So let's first analyze that part. Starting with the half, if I multiply by 2, I get 1, multiply by 2 again, 2, by another 2, I get 4, and followed by 8. And then it asks, well, what is the multiplier as you move toward the right? Now, obviously the inverse to multiplication is division, so you might have been thinking about, okay, 16 divided by 2 would give me 8, which is a true statement. But when we talk about the multiplier, dividing by 2 is the same as multiplying by a half. So we could see this here. We're going to multiply a half by a half. That's how we're getting a 4th. Multiply by a half again, we get an 1/8. Multiply by a half again, we get 1/16. Let's finish filling in the exponent form. Now, some of these you might have just reasoned through because you knew in comparison to 2 to the 4th what some of the others had to be. So you would say 2 to the 3rd is equal to 8, 2 squared is equal to 4, 2 to the 1st is equal to 2. And you start to notice this pattern, right? Every time we are multiplying by a half, our exponent is getting smaller by the value of 1. And so that pattern continues. So let's just kind of analyze the pattern before we answer the remaining questions. So let's look at 2 to the 4th and 2 to the negative 4th and their values. So 2 to the 4th is 16. 2 to the negative 4th is 1/16. This is kind of familiar to some of our previous lessons. The only difference is in the previous videos that we looked at, the bases were all 10. Now we're looking at bases that are all 2. So as we continue this pattern, look at 2 to the third and 2 to the negative third. The values are 8 and 1 over 8. Moving forward, your values here are 4 and 1 over 4. And here we have the value of 2 and then a half for 2 to the negative first. And then that power of 0 is still giving us that value of 1. Similarly to everything we saw in the previous videos with powers of 10, now we're just looking at exponents that have powers of 2, and you'll see in a moment how these all kind of relate in terms of their structure. So let's continue answering some of these questions. Use the patterns you found in the table to write 2 to the negative 6 as a fraction. Well, if we were to continue that comparison, 2 to the negative 6 is the same as saying 1 over 2 to the 6. Which again, we're multiplying a half times 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 a half. So 6 times, that's 6 factors that we're multiplying together. Or we would just write that as 1 over 64. In problem 3, it asks us to write 1 over 32 as a power of 2, right? So we're using that base of 2, we're using powers of 2 instead of powers of 10 with a single exponent. It would look like this. 1 over 32 is the same as saying 1 over 2 to the 5th, so multiplying a half together 5 times. And then we know that relationship between those positive and negative exponents. So with that single exponent, we would write it as 2 to the negative 5th. What is the value of 2 to the power of 0? We already said that that's equal to 1 still. Anything with the power of 0 will always give us 1. And then from the work that we've done with negative exponents, how can we write 5 to the negative third as a fraction? So 5 to the negative third is the same as 1 over 5 to the third, a fifth times a fifth times a fifth, which is 1 over 125. And the last question, how would you write 3 to the negative fourth as a fraction? 3 to the negative fourth is equal to 1 over 3 to the fourth, or we would write that as 1 over 81. So in following up, how does working with powers of 2 compare to working with powers of 10? So the properties apply in the same way, but computing the value of the exponents is more difficult. What happens when you use exponent rules when one of the exponents is 0? The rules apply the same way. So when that exponent is 0, we said that it's equal to 1. You can see this here, how they relate. How does 10 to the negative third compare to 2 to the negative third? Both values are positive and less than 1. Since 10 to the negative third has greater numbers in the denominator, it is less than 2 to the negative third. So again, each of these expressions are telling us we're multiplying a tenth times a tenth times a tenth versus a half times a half times a half. So before we said this, we said 10 to the power of n times 10 to the power of m. We would add those exponents together. Those rules still apply, but we're just going to broaden the spectrum of what we're applying them to. So now we are going to say that x to the power of n times x to the power of m will still remain that same base of x, but you're going to add those exponents together. So in this previous activity, our bases were 2, and we were using powers of 2, so we said a half times a half times a half, or a half times a half times a half times a half. Whatever that exponent was is how we were using it. So again, revisiting this criteria, we want to use the exponent rules for bases other than 10, which we just were introduced to. In this next activity, we're going to basically analyze some situations and look at exponent rules with bases that are other than 10, which is what we just discussed. So in this situation, Lynn, Noah, Diego, and Elena came up with a list of expressions. Some are equivalent to the original and some are not. For each list of expressions you choose to analyze, decide which expressions are not equivalent to the original. Take a moment, pause here, go through those lists, and then you can cross them out, circle them, whatever you would like to decide which ones actually don't fit the criteria that each of them are working with. Now that you've had a moment to pause the video, let's go through Lynn's list. So Lynn actually had 3 items in her list that were not equivalent to the original expression of 5 to the negative 9. So the first one that was not equivalent was negative 5 to the ninth. And again, that goes back to the warm up of the that negative, right? So the 5 is your base, it's being raised to the power of 9, but that negative kind of affects the way that it's working. The next one that's not equivalent is 5 to the third raised to the power of negative 2. If you apply the rules, that would be equal to 5 to the negative 6. And the last one that's not equivalent is this one here, and that's because when you subtract those, you end up subtracting negative 4 minus negative 5, which is equal to a positive 1. So just be careful there with those subtractions and negatives because that's a very common mistake. In Noah's list, his were having to be equal to 3 to the 10th. He had 2 that did not belong in his list. This first one here did not belong because when you add those exponents together, you end up with 3 to the 7th. And the other one that did not belong was the last one. Common misconception is that we think to divide the exponents, which is not true. If you see the previous one, you're actually subtracting. That's why this one here is true, but the last one is not. The last one gives you 3 to the 18th. In Diego's, he had 2 that were not equivalent. This was the first one. This would actually give you x to the negative 12. Again, you're subtracting here. I believe, actually, hold on. I think in your books, I think maybe this is typed wrong or screenshotted wrong, but I believe in your books, it's a positive 8. So that's, oh, I have the wrong one crossed off. That's why. Let's fix that really quick so there's no confusion here. It should be that one. Okay. So there we go. Now that will make a little bit more sense. That one does not belong. And then the other one is this one here because that would just be equal to 4x. And the last one, this is the only one that doesn't belong. All of the other ones will give you 1 because their exponents are all 0. Okay, so in just kind of summary, we saw before that 10 to the third shows the repeated multiplication and 10 to the negative third shows what's listed here. How does 2 to the third and 2 to the negative third compare? So we would basically now say we're doing 2 times 2 times 2 versus 10 times 10 times 10, and then a half times a half times a half versus a tenth times a tenth times a tenth. So how do these compare here? The exponent rules work in exactly the same way. The base is just 5 instead of 10. So again, all the rules still apply. You just have different bases. Do the other exponent rules work the same way as they did for the base of 10? And that's our conclusion here is yes. So we can look at the quotients. We are still subtracting. The products, we are still adding those exponents together. What about something like this? Do we agree with this example here? And we would say no, because you cannot combine bases in this way. The left side has 5 factors that are 3 and 3 factors that are 4. The right side has 8 factors that are 12. So they're not equal. So remember that those bases have to be the same to apply those rules. Exponent rules with other bases work exactly the same way as they did with 10, as long as, again, you keep those bases the same if you're applying the rules. You can read through the lesson summary if you choose. Otherwise, you are successful if you can use the exponent rules for bases other than 10.